For today, we are left with only one thing. We only have to do one more thing, and that's it for the theory. We have to prove Moivre-Laplace theorem, right? So let me write that over here. So we have, as you remember, we have two different versions of Moivre-Laplace. So local version of Moivre-Laplace theorem. So this one, we wrote it like this. So we had some sequence of random variables xn. So here it's important to understand that we don't have one random variable xn, okay? We have a sequence, okay? So we have x1, x2, x3, x4, and so on. So n tends to plus infinity here. So we have that xn has binomial distribution with parameters n and p, okay? And we needed a function, a sequence phi of n, to be little o of n to the power 2 divided by 3. Okay. So the first question that I ask in the exam, if you have this question, is why do we need this? So if you don't answer this question, that's it. Like it means that you don't know the proof. So we have the sequence of random variables. We have this function, and then we can state the following: that the supremum over, so we have the supremum over all k non-negative integers such that k minus np is bounded by phi of n. Okay, so the supremum over all possible values of k here. So k, of course, is the number of successes that we have in the Bernoulli trials. And then we had that the probability that xn equals k divided by the following function that should be very easy for you to remember because, well, you know normal distribution, right? So you should remember that here we should have 1 divided by the square root of 2 pi. And then we have sigma squared, so the variance of binomial distribution, right? We know that the variance is np times 1 minus p. And then we have e to the power minus, so in normal distribution we have minus x minus the expected value square, so minus k minus the expected value of binomial distribution, which is np. All of this is square, and 2 times sigma square, so 2 times the variance, which is np1 minus p. Right? So yeah, that's why it's not difficult to remember this. So this minus 1, so all of this expression minus 1, right? So this converges to 1. This relation converges to 1. So this converges to 0 as n tends to plus infinity. Okay, so this is Moivre-Laplace. And again, let me remind you that before Moivre-Laplace, we had Poisson limit theorem. So the question here is so I want to find the probability that I have k successes, but in this case, the number of trials tends to plus infinity. So in the first case, we had that the probability p, the probability of success, was a function of n. So p was a function that was very small, right? So p tends to 0. If p tends to 0, then we have Poisson limit theorem. And we have that then binomial distribution is Poisson distribution in the limit, okay? Binomial distribution becomes Poisson distribution if p tends to 0. Now, if p is constant, then we have that binomial distribution is normal distribution somehow, okay? So that's the idea. Okay, so let's prove it. Right. Well, we have to prove it, and we'll see it across the way. Which one? This one. So look, this divided by this is about 1. So this is equal to this, about, right? So we have that somehow a divided by b is about 1. So a is about b, okay? So that's the idea. Right, so let's prove it. So the proof is going to be formal. So the formality of the proof is going to be about 90%. Let's say it like that. Okay. So I will skip some moments. Well, because we don't need that kind of formality here, but it's still it's quite formal. So we need to find the probability that xn equals k. Right? Probability that xn equals k. We already know what is the probability that xn equals k. What is the probability that xn equals k? Mm-hmm. Yeah, so this is just n choose k, p to the power k, 1 minus p to the power n minus k, right? So we already know this. Now we need to find that this, if n tends to plus infinity and p is like this, then this is about this function, okay? So this is what we need to prove. So what is n choose k? We know that n choose k is? Yes. Yeah, and then we have p to the k, 1 minus p to the n minus k. Right? At least we know this. Now, the key moment is the next one, okay? Because we have the factorial, and the factorial is a very well known function in mathematics. So we already know, for example, what the gamma function is, right? We have been working with the gamma distribution, and we know that the gamma function is just the factorial somehow, right? So we already know how to work with the factorial, but there's one formula for one approximation. So like the best that I know of for the factorial that we have to use right now. I think that you should know this approximation. What approximation do we know for n factorial? Yes, exactly. So how do we call that? The Stirling's approximation, right? Stirling's approximation. Do all of you know about this? Stirling's approximation. Where do you know this from? Calculus, or? Yeah, I think you had this in calculus, maybe, or in discrete math. No? Yeah. Okay. Now it's a time. Yeah. Finally. Yeah. Now this is a very important formula. Stirling's approximation is used, and so in this field of probability in calculus, in which we have to always work with n tending to plus infinity, we will always have to use n factorial. I mean, Stirling's approximation, because n choose k is everywhere. And we don't know how to compute n choose k. I mean, the best way that we have to compute n choose k is using Stirling's approximation. And n choose k is absolutely everywhere, okay? So look, we know that the square root of n, sorry, not the square root of n, but n factorial is about, okay, let me write, is equal the square root of 2 pi n, right? The square root of 2 pi n. What's next? N divided by e to the power n. And we can write it like this: 1 plus big O of 1 divided by n. Big O. Right. So this approximation works really good for n tending to plus infinity, of course, but this actually works really good for n equals 5. So if you have the graph of this function and the graph of this function, they are very close at very low values. Like for n equals 3, 4, they are very similar already. So n doesn't have to be 1 million so that this becomes true. Okay, so n can be only 10 or something like that, and this is already true. I mean, they are very close, right? So all that we have to do right now is to replace this right there. And yeah, that's like the key moment of this proof, okay? So the key moment is Stirling's approximation, right? So this becomes, let me write over here. So n factorial is the square root of 2 pi n divided by e to the power n. And let me write this by now so that I can write equal here. And then in the next step is when we lose a little bit of formality, but let me keep it like this. Okay, so this is n factorial. Then we have k factorial. Then we have n minus k factorial. Good. So this is n choose k, the approximation for n choose k, okay? And then we multiply this just by p to the k. So let's keep this p to the k. I think I wrote this very huge. I had to, that's it. It's over the space. P to the k, 1 minus p to the minus k, okay? All right, I think that nothing difficult by now. Now look, what can we cancel here? So first we have e to the n, e to the k, e to the n minus k. So we can cancel this e to the k here with this e to the minus k, and this e to the n with this e to the n. So actually we don't have any e. We don't have this e, we don't have this e, we don't have this e. Now next, the square root of 2 pi, I think, right? But we are left with 1 square root of 2 pi. That's good because, look, we already found something. This is square root of 2 pi. We found it already. Okay. Now, what else? Well, I think that's it. Like, let's see what can we write next. So this is equal to the following. I will have 1 divided by the square root of 2 pi. Yes, 1 divided by the square root of 2 pi. And then I have the square root of n and n to the power n. Okay, square root of n. And let me write n to the n later. Okay, so I'm not going to write, look, I'm not going to write here equal. I'm going to write like this. So approximate is equal to this. All right, so I'm going to forget about this big O from here. And we just have to understand that since n tends to plus infinity, then this becomes this, okay, if n tends to plus infinity. All right, so this is where we lose a little bit of formality, but it's okay. Okay, so and here we have k to the power k, the square root of k from here, and from here we have the square root of n minus k. And now I can write this n to the n, k to the k, and n minus k to the n minus k. And then p to the k, and 1 minus p to the n minus k. Good. Now let me do the following. Let me see at this property, at this condition right here. And let me say that let p, let k, yes, let k, where can I write here? Okay, here. Let k be equal to np plus phi of n. Phi of n is little o of n to the power 2 divided by 3. For this k, this holds. Okay? For that k, this holds. So we are going to take this value for k. And now let me divide everything by n. So from here we get that k divided by n equals p plus little o of n to the power 2 divided by 3 divided by n. So 1 divided by n to 1 divided by 3, yes? So since n tends to plus infinity, then this just tends to 0, right? So we have that Kn is about P. K divided by n is about P. And if we think about it, this makes sense because K is the number of successes that we have. N is the number of trials. Then if we divide the number of successes by the number of trials, this should be the probability of success, right? So K divided by N should be about P. And now that we have that, then I want to get everywhere K divided by N so that I can replace this later by P, okay? So I want here K divided by N and here N, well, something depending on K divided by N. So let's multiply and let's divide by the square root of N to get that. Square root of N here, square root of N here. N to the power, what? We chose it so that this condition holds. So for that K, this is true. Here, we multiply and divide, right, by the square root of N. So this is 1, so it's okay. So what do we do first? So first we keep this. So we'll have the square root of 2 pi n, which is this. So we already have part of the answer. So this is going to be, well, here we have equality, right? So we have 1 divided by the square root of 2 pi n. Yes. And then this square root of n is going to divide this k. And this square root of n is going to divide this n minus k. So we'll have 1 divided by the square root of k divided by n. And the square root of 1 minus k divided by n. Yeah. And now the next step is the following. So instead, let me write k like this. So let me write minus, so here I have n. So n minus k plus k. Minus k plus k. So I can do the following. So this will be, so first I will have n divided by k to the power k. And then I will have n divided by n minus k to the power n minus k. And multiply by p to the k, 1 minus p to the minus k. Right? What do we do next? Well, next, we already obtained that k divided by n is about p. So I can say that this is about 1 divided by the square root of 2 pi n, 1 divided by the square root of p times 1 minus p. So this is from here. So we already have this part. This part right here. We already found that. And now everything else should be e to this power. E to this power. So how can we do that? So let me write this in the following way. So look, I have n divided by k to the power k and p to the power k. So let me take that together, okay? So let me take that in the following way. P divided by k divided by n, sure, yes, p, or, okay, this to the power k, k divided by n, sorry, here, k divided by n. And then I will have here 1 minus p by 1 minus n minus k divided by n. All of this to the power n minus k. Like this. All right? Now, I want this to be e to some power. And what do I do if I want that to be e to some power? I made it e to some power, right? So this will be equal to 1 divided by the square root of 2 pi n p times 1 minus p. And this will be e ln of this, right? So let me take it like this. So I want n divided by k, right? Because no, I have k divided by n, k divided by n. So let me take this k divided by n. So I will have this, look, k divided by n divided by p to the power minus k, because I changed the order. Since I have this product here, then this will be a sum plus. And now this, again, I will have ln of 1 minus k divided by n divided by 1 minus p to the power minus n minus k. Now, this is equal to the following. 1 divided by the square root of 2 pi n p 1 minus p. And by the properties of ln, I know that I can take this here to multiply, right? And let me multiply and divide everything by n. So it will be like this, look. E to the minus n, and I will have k divided by n, ln of k divided by n divided by p, plus 1 minus k divided by n, ln of 1 minus k divided by n divided by 1 minus p. Yeah. Well, finally, I have obtained here a function that depends on k divided by n. Yes. All right. This is some function. This is some f of k divided by n. Some function that depends on k divided by n. Now, let me find an approximation for this function using Taylor's series. Okay. So let's use Taylor's series so we can find an approximation for this. So what is Taylor's series? What is the Taylor's approximation of a function? So let's find the function around the point P. Okay. So look. So f of x. So how can I express f of x using Taylor's series? This is a sum from 0 to plus infinity, right? Derivative. Well, in this case, I want to use not in 0, not Maclaurin's form, but in some point P, right? Multiply by right? So we all know this. Now let's apply this to find an approximation for that function. So what is the zero derivative? It's the function itself in the point P. What is the function in the point P? So f of x, so let me write here, by the way. So we have our function equals the following. So f of x equals x by ln of x divided by p plus 1 minus x and ln of 1 minus x divided by 1 minus p, right? So what is f of p? Zero, yes, zero, right? F of p is zero. Why? Because we have ln of 1, and the natural logarithm of 1 is 0, right? And in that case, we also have ln of 1. So f of p is 0. Next, we have to find the first derivative, right? So first derivative in the point x. Well, let's find it, right? So we have 1 plus ln of x divided by p, yes, minus 1 divided by 1 minus x plus x divided by 1 minus x minus ln of 1 minus x divided by 1 minus p. Okay, now this looks better, right? Okay, so what is the first derivative in the point P? Yeah, well, it should be 0. We have here 0. Here we have 0. Here we have what is this? This is equal to 1, right? Because we have x minus 1 divided by 1 minus x. Yeah, so 0. Okay, so actually we don't have this 1 here. Yes, we can. Yeah, so like this. So we can write it this like ln of x divided by p minus ln of 1 minus x divided by 1 minus p. Yeah? X minus 1 minus... Yeah, do all agree. Okay. Now let's find the second derivative. Point x. So again, we have 1 is going to be p divided by x multiplied by 1 divided by p minus 1 minus p divided by 1 minus x multiplied by the derivative, which is minus plus 1 minus p. So we cancel this with this, and we obtain that this is 1 divided by x plus 1 divided by 1 minus x, which is equal to x, 1 minus x. We have here 1 minus x plus x of 1, right? So we have that the second derivative in the point P is equal to 1 divided by P times 1 minus P. And finally, we can use Taylor's approximation to say that f of x is going to be equal to the following. The second derivative in the point P, which is equal to this, 1 divided by P times 1 minus P, by x minus P squared, well, divided by 2 factorial, so by 2, times x minus P squared. Plus, what should I write next? Plus what? Yes, because of, and this is very important because this is the moment where we are going to use this condition. Okay, so because of x minus p to which power? Third power. Yes, like this. So we have found f of x. We just need to replace that over here. Instead of x, we need to write k divided by n. Let's see what we get. So here we have this square. Do not forget about that. Okay, so we have the following. So we continue with that equality. We have that this is equal to 1 divided by square root of 2 pi p 1 minus p, and e to the minus n, and we have f of x, so f of k divided by n. So we'll have 1 divided by 2p 1 minus p, and x, instead of x, we need to write k divided by n. So we have k divided by n minus p squared plus big O of k divided by n minus p to the power 3. So we are very close to the end, right? So this is equal to 1 divided by the square root of 2 pi p 1 minus p. And what do we have here? So let's see. So we'll have, this is what? This is k minus np divided by n squared. Yes? This is minus e to the minus k minus np squared divided by n squared, but here we have n, so we keep only one n, so 2 times np 1 minus p, which is exactly what we have right here, right? But we still have something else. So let's see what happened with that something else. So plus, and here we have k minus np divided by n to the power 3, but here we multiply by n. So we'll have big O of k minus np divided, so this will be to the power 3, yes, and n squared because of this n. But we know that k minus np is what? Yes, so this is bounded by little o of n to the power 2 divided by 3. So we cancel this 3 with this 3, and we obtain that this function is little o of n squared. So we have that all of this will be little o of 1. Because we have, n squared, so we'll have here little o of n squared divided by n squared, so little o of 1. So little o of 1 is a function that tends to 0. So the whole thing, all of this, tends to 0. And this is why we need this condition. Okay? So that's it. So we can approximate this by 1 divided by the square root of 2 pi and p1 minus p e to the minus k minus np squared divided by 2 times np1 minus p. Done.
Is it an approximation or is it an exact?
It's an approximation. So here I could write exact plus big O of something that tends to 0. But since we don't want to write that, like we don't need it, right? So we can write that this is approximation. Okay? Any questions? Good. So this is the local Moivre-Laplace theorem, the one that we don't use in practice. Now, we need this one to prove the one that we need in practice, right? Which is the integral version of Moivre-Laplace. So let me write the statement, and then let me prove it. And that will be it. Okay, so let's. Now, second one is the integral form. Of Moivre-Laplace. So we have that, again, xn is a sequence with binomial distribution and parameters n and p. And then we can state the following, that the supremum over all, so we have 2 A is less than B, and these are real numbers. Okay, so the supremum of A less or equal than B, this is less or equal than plus infinity, this is greater or equal than minus infinity. And then I will have the following, so that the probability that xn minus np divided by the square root of np1 minus p, the probability that this is from A to B, we can approximate it, so here minus the integral from A to B of 1 divided by the square root of 2 pi e to the minus x squared divided by 2 dx. This supremum tends to 0 as n tends to plus infinity. So what do we have here? We have that the probability that this random variable, let me call this the random variable eta. Okay, so first it's very important to notice that here we are not talking about xn. Here we're talking about some form of xn, like we have xn minus np and divided by this. Okay, so this doesn't give you the probability that xn equals something. Okay, so don't get confused. This is not the probability that xn is from A to B. This is the probability that xn minus np divided by the square root of np1 minus p is from A to B. Okay, now let's understand what is here. So we already know that this, what is this? This is the density of some random variable xi, where xi has what distribution? Standard normal distribution, right? So what is written here, this integral, this is the probability that xi is from A to B, right? So to compute the probability that this eta is from A to B, we have to compute the probability that the standard normal distribution is from A to B. So this random variable in the limit, now here, in which limit we don't know yet, we will know this in 5 months. This is xi. So this random variable eta converges, and we will call this in distribution to xi. Okay, so we can approximate this random variable with xi. All right. So why do we need minus np and divided by this? Why do we need that? Let's understand so that you remember this by heart. Yeah, because look, so what is the expected value of xi, of this xi? Well, we have that today, right? Yeah, but still, what? No, we already discussed that in the lecture. So what is the expected value of xi? 0, right? So we already proved that if we have some normal distribution, then A, so the number right here is the expected value, and sigma squared, the number right here, is the variance. So here we have that the expected value is 0 and the variance is 1. Yes? Now, what is the expected value of eta? 0. Yeah, of all of it. So the expected value of xn is np. That's why we have np minus np, so the expected value of eta is equal to 0. So we made this so that at least the expected value and the variance coincide, right? So they should be the same. And we divide by the square root of np1 minus p, because this right here is the variance. So we divide by the square root of the variance so that the variance of eta becomes 1. So we transform this so that the variance becomes 1 and the expected value becomes 0. Yeah. We have xn. The expected value of xn is np. It makes sense that if this something converges to this, then the expected value of this xi and the variance of this xi should be equal to the random variable that is converging to that random variable, right? So the expected value of this should be 0. To make a 0, we have minus np. To make the variance 1, we divide by the square root of np1 minus p.
just Stirling's approximation? That e to the power, or is it something else?
So the probability that this is from A to B can be approximated using the integral from A to B of this.
What is this?
This is the PDF of a standard normal distribution. Okay, so I hope that the idea is clear, right? So this is, here we can see that if P tends to 0, then binomial becomes Poisson. If P is constant, it's about constant, so it doesn't tend to 0, then binomial becomes normal. And actually, not only binomial, but almost any distribution with expected value and variance becomes normal. This is one of the most important theorems in probability theory called the central limit theorem, that almost any distribution becomes normal distribution. Okay? Central limit theorem, CLT, the central limit theorem. So if you want to understand the idea of this, like the intuition, so you can find on YouTube a lot of videos about the central limit theorem. They have really good examples, simulations, I don't know, something like that. Okay, so let's prove it. Actually, the proof is quite easy compared to the previous one. So look, we just have to say that this probability can be approximated using this integral. So look, let me write then the probability that xn minus np divided by the square root of np1 minus p is from A to B. From the local Moivre-Laplace theorem, I know the distribution of xn. Then I want to have xn alone. I don't want to have it minus np divided by that. So I need to have xn alone. So this is equal to the probability that xn is from, I think xn, yeah, like this, xn. Then I will have a multiplied by this, a multiplied by np1 minus p, plus np, right? And xn is at most b multiplied by the square root of np1 minus p plus b. Plus np. Yeah. Now let me call this interval, like, let me call delta is the interval, this interval. So a times np1 minus p plus np and b times square root of np1 minus p plus np. So delta is this interval, okay? So this probability can be computed as the sum. I know that xn is number of successes, so xn is a non-integer, is a non-negative integer, a non-negative integer. So I need to find the probability, so the sum of the probabilities. So I will have the probability here that xn equals k over all the integers inside this interval. So over all k inside this interval, right? So I need all non-integers, all non-negative integers inside the interval delta. And then right here, I need to use the approximation that we know from Moivre-Laplace, the local theorem, the local Moivre-Laplace. So here, let me write by local Moivre-Laplace. We know that this is going to be the sum. And now let's do the following. Let's change the variables. So let me call, where? Here. Y is going to be, what exactly? Let me see. Well, I want here A. I want here A. So I need minus NP and divided by that, yes. So Y will be K minus np divided by the square root of np times 1 minus p. Okay, so I will have a new variable y. And then this becomes this right here. So the new interval, so for every, let me call here, for every y in delta. Y in delta. So what is, if k equals this, then what is y? It's going to be a, right? Because we have this minus np, so we don't have this. And then we divide it by that, so we cancel those, so we have a. So this, you write like this, y is in delta, so we have the sum from a to b of, so from modular Laplace, we know that this is 1 divided by the square root of 2 pi np1 minus p, and e to the minus, and then we had k minus np squared divided by that, right? So we'll have y squared divided by 2. Yeah, let me see. Yes. All right, so if you replace y, you will have here k minus np squared divided by 2 times np1 minus p. So this is modular Laplace. Well, we're close. Now, what is the point? Look, what do we have here? We need a sum from a to b of this. So we know this is a, this is b, and here we have this function that goes like this. So this is e to the minus y squared divided by 2. And here we can divide it by the square root of 2 pi. So this sum right here, this sum, we are multiplying this by 1 divided by the square root of np1 minus p. So I can divide this into segments such that the length is 1 divided by the square root of np1 minus p. Since n tends to plus infinity, then this tends to 0. So we are multiplying the length of this that tends to 0 by the height of this function. So we are getting this plus this plus this plus this whenever the length of this interval tends to 0. And we know that that's the integral, right? That's the Riemann integral. So this can be approximated right here by the integral from a to b of this function. That's it. Any questions?